back to the workshop. So, components that we're going to be using today. Other than your breadboard and LEDs and wires, which are pretty much assumed to be a part of every single workshop, three new components that we're looking at today. A potentiometer, which is the thing that looks like sort of like a volume adjuster, if you will, in your kits. So I'll see if I can find one to show you, because I don't have a picture up at the moment, but we do have pictures later in the slides. This is what a potentiometer looks like. It's got 3 pins and a little dial which you can twist. So basically it acts as a voltage divider and variable resistor all in one. So these things have a resistance of 100 kilo ohms for those of you that are interested. An Rgb LED, in each of your kits you should find I think 1 or 2 of those. They're LEDs with 4 pins. So if you find an LED looking thing that it's clear and has 4 pins, that's an Rgb LED. We're going to be using that today. And the other thing that we're going to use is a light-dependent resistor. So these things are also quite small. They're used as light sensors. I'll see if I can dig one up from somewhere around. Maybe I have it. Do I have it around? That's a potentiometer. That's what the light-dependent resistor looks like, but it's really quite small. We'll be using those components today. All right. Anyway, going back to analog write or analog read rather. So we'll start off with analog read because this is, I guess, news to get you guys started. Again, you can follow along with workshops at your own pace. But essentially, with analog read, this is a function that only has one input, spelled analog, capital R read, all one word, as you see up there. The input is the pin number. So it's important to note that when we talk about pins on our Arduino, we're going to be using for the first time today our analog input pins. So they are on the screen, they're A0 through to A5. They're next to the power bank, and they'll be all the same as the Arduino Mega board, except the Arduino Mega board has like almost more than twice as much, I think, as the Arduino Uno. So analog read returns an integer, which is a number between 0 and 1023, which corresponds from 0 to 5 volts. So you can also scale it in the Arduino program to be like another scale, but we won't be worrying about that too much today. The pin number is A0 to A5 for a Uno or more for a Mega. You can also use 0 to 5. You don't have to have the capital A there, but just be aware that when you're analog reading, it's not from your normal digital pins. And it does take, there is a limit to the time at which you can poll analog input. It's about 0.1 milliseconds, so you can poll an analog read at 10,000 times a second, which for some people might actually be a bit slow, but that's the way it goes. So the first thing we're going to do today is get a variable input connected to our Arduino to get this to work. So we have on the slides here a very, very simple circuit. And I'd recommend don't try, obviously, connecting the wires directly without a breadboard. Plug your potentiometer into your breadboard and wire it up from there. So what you do is you simply connect, you have your 3 pins on your potentiometer, and because it's a linear potentiometer, the voltage dividing is going to go quite smoothly as you turn the potentiometer. The dial on the potentiometer. Basically, it needs to be a powered sensor, so a lot of analog input sensors are powered, obviously, because you're scaling from 0 to 5 volts. We're going to make the Arduino provide the 5 volts to our potentiometer on one side. It doesn't matter what side it's in. On the other side, you're going to have a wire going back to ground, and in the middle, you're going to have a pin going to analog input. So, for example, analog input 0. So it's quite a simple circuit. All you need is a breadboard, this potentiometer, plug it in, make sure that you plug it in so that each pin is in a different row, and then just wire one side to 5 volts, the other side to ground, and the other side to 0. So what I'm going to do now is show you what that looks like when you end up turning it. Basically, once you've got that there, we'll go into our Arduino environment, which I'll pull up now here. Preferences. Let's try 20. Okay. Wow, that's really quite small. Step it up to 48. Too high res. Okay, perfect. All right, so once you've got that circuit set up, void setup, perfect, thanks. Void loop. It's the first thing I do for every Arduino program. Now, to understand what's happening with our potentiometer, you don't need to define analog inputs as inputs with pin mode like we did last week. We only, because they're always going to be inputs, they don't need to be defined. The only thing that I think we need to do in setup is to begin our serial communication so that we can view the output of our potentiometer. So all you do is do a serial.begin in there as usual, like last week, and then in void loop we're going to have just simply one line of code to get this to work. We're going to have a serial.println so that we can read it nice and easy, and we're going to put an analog read in there, and pin 0 or A0, it doesn't matter how you write it, and that's our program to get us started. So all we're going to do is wire that up, connect your potentiometer, and get your serial monitor open and see if that can, if you can get that working, which shouldn't be too difficult. I'm just going to make the circuit and upload the program now. Oops. I think you may have to again fiddle with the ports to get this to work. Now, while I have nothing connected to my Arduino, I'm just going to get junk coming out. I haven't got anything connected at the moment. But when I do get something connected, which I will very shortly, 5 volts, ground, and analog input, hopefully something will appear now. Yes, okay, cool. So if you give your potentiometer a twist one way and then the other way, you should note that the reading goes all the way from 0 up to 1023, like that. So that's a really easy way to get analog input straight into your device. So just electrically how it works is that you've always got a resistance across the outside pins of the potentiometer of 100 kilo ohms. That's fixed. However, the middle pin, how I guess the resistance across the two pins adds up to 100 kilo ohms, but that divide, the way it divides across those like 3 pins, is adjusted by your rotary potentiometer. So you can make the connection between one pair of pins 0 and the other pair like 100 kilo ohms, or you can make it half and half, or you go all the way to the other end. That's what rotating the potentiometer does. So that's how we get variable input. So hopefully that didn't take you guys too long, but I'm going to move on for there. Just close that off because we've got a lot to get through today. Just see who got that working successfully. Yes? Good? Awesome. All right. So that's an example of like how you could do it. Actually, that shouldn't be there. Don't you don't need to pin mode the pin to an input. That line shouldn't be there. So we don't need to actually make something an input, but just illustrating how that works. Be aware there might be some errors in the sample code here. I should get rid of them. So how analog output works. So in terms of pulse width modulation, I explained this very briefly last week, but we've got like a diagram to illustrate on the slides today what's happening with pulse width modulation. So it's riding constantly between 0 and 5 volts. However, you can adjust the width of like the cycle that's high, and therefore essentially create a variable voltage that way because it's pulsing so fast it averages out over time. So on your Arduino, as I mentioned, you can see which pins are labeled pulse width modulation on the top on the digital bank there. So we're going back to the digital bank and the ones with the squiggle next to the pins. On the Uno or on the Mega, I think all the pins from like 2 through to 13 are pulse width modulated, or even more than that, I think. So again, how the function works, we get to analog write a pin to a certain value between 0 and 255. Just note that the range is different than the analog read. So your analog read value returns 0 to 1023. Your analog write return output 0 to 255. That's, again, the scale from 0 to 5 volts is just divided over a different interval. And that's essentially how analog write works. So what we can do is you do have to select a certain pin as an output when you're analog writing digitally. And that's what we did last week, or one of the things we did last week was sweep an LED from 0 to 255 using that code with a for loop to get the results that we want for adjustable brightness. Now, before we go into another practical task, just going to teach you guys one more function, and that's the map function. So we've got the map function. What it does is it scales between two different numbers, a number that's between two different numbers, to adjust it so that it's within be in the same place within another scale. So why this is useful is that obviously, if for example you have an input that's reading from 0 to 1023, you want to scale it to an output that's 0 to 255. How do you do that? Well, an easy way you can do that is just simply divide that by 4, because that is the approximate scaling. But if we really want to get a precise number, then we can use the map function. So what we can do is it returns the number which after it's been mapped, and the input the first input is the number which we're mapping, and then the low and the high range of the original scale which is being mapped from, and then the low to the high range of the scale that it's going to. So note that they don't have to necessarily be like high and low. We can flip them, for example, in the second one, or we can make it larger than another to get that kind of scaling effect that we want. So that's how that function works. Again, if I'm going slightly too fast, we do have the slides online, but I'll make sure we go at another decent enough pace. The other thing is an easier function, which I want to illustrate, which is the constraint function, which maps an integer, doesn't map an integer, it constrains an integer between two different values. So this one's more self-explanatory. You've got an A and a B, which are your low and high values, and you're constraining a number to be between those two values. So, if x is less than the low value, then it will be made equal to the low value, and if x is above the high value, it will be made equal to the high value. It's sometimes good to have this in your program when you say pulse width modulating. If you want to make sure that your functions don't ever go lower than 0 or higher than 255, the constraint will often ensure that it's a great sort of fail-safe to make sure that you don't get any strange input into your functions. Anyway, the first task that we're going to do today, challenge, I do have the answer on the next page, but don't worry about it too much, is that we're going to adjust the brightness of an LED with the potentiometer. So just as a refresher for you guys last week, if you've forgotten how to wire up an LED, I got a lot of questions about the resistors weren't the exact same as in the diagram, or I was a bit scared about which resistor to use. Generally speaking, you can't destroy your LED if you're using a resistor that we provided you. So if you haven't got a resistor, put up your hand. But if you do have a resistor, you can't get it wrong. It'll just be your LED is slightly dimmer than you want it to be, in which case you can swap the resistors around to get the brightness that you want. So give you guys a couple of minutes to get that happening. Basically what you want to do is you want to get your input from your potentiometer, as we just did before, and map it with an analog write to your output.
Could we have a prize for the person who does it first or something?
Nah. Because otherwise, some people already are really good at stuff. Yeah. I don't want to make this feel. Just gonna make sure that.
Could be like any person. Yeah, it should be. Do you want me to start? Oh, do you have
By the way, the solution was originally incorrect. So if you guys are looking at the solution, maybe don't copy the solution straight away. If you guys do want to see the new solution that I've just fixed up, you can hit refresh and go to the next page. Also, if you guys don't have Arduino kits, we do have some spares today. Also, if you haven't picked up your Arduino kit yet, I think we have one guy that hasn't. Yours is obviously ready to pick up.
Oh, 7 years, yeah. 7 years.
Yeah, that's right. Why doesn't it go all the way down? High transition components inside. To be honest with you, so I haven't done that, but yeah, I just look very closely at components and how they react to the low to high transition. Obviously, like there might be some logic gaps. Cool. All right. You guys another week or two.
Also, there's like 3 drives on the board, and they're all.
Put up your hands if you have got it working successfully, by the way. One. Okay, we'll wait.
Did you get it working? Well, if you struggle, let me know. Okay? Like our innovation. I'm going to take some photos. I was just about to say. Do you want to take pictures or?
Yeah, I'll take pictures.
Do you use a fancy camera?
Yeah. Actually, yeah. You got explain what this is about on the next slide. So for this particular one, we've chosen LED to the output LED to be pin 11. So just be aware that the reason we've done that is that it's pulse width modulation and it enables on both Unos and Megas. Well, I'll make sure they get it working once it's possible, just to explain how the solution works. So what we're doing, of course, is we are reading a value from our analog pin, that is from our potentiometer as wired up before, and then we need to define an integer x in the problem. So we've one more error with the solution. So we need two integers to deal with. We need our input and our output. So just remember that integers, at least for now, are easy enough to be defined globally rather than within functions. So we have an integer x, and we are mapping the value that is a result of our analog read, which was originally from the scale of a 0 to 1023, and we're mapping that to be between 0 and 255. So what that's going to do is give us a nice little linear transition from having our analog input to our analog output. And then we are analog writing to the LED. Again, sorry, another error that I've spotted. All right. I really should have gone through these slides more closely. Of course, we are analog writing the result of the map, not the input into the map. So that's how that would work. Just make sure that everyone can get that happening before we move on. Yeah, if you have any questions, please just put it in your hand.
But I don't have give it a try because these computers are different. They're a bit different. Yeah, yeah, I think so. Yeah, do you mind the
Sorry, I'll unhook this sign. Making your own light sensors essentially, and also using potentiometers as analog input. So, wait, were you around last week? Yeah.
I will let you know online.
Okay, cool. Yeah. So, yeah, we've got what's happening on the slides so far, but basically we've connected one of these things up, and we've got it happening into our analog input, and we're controlling an LED, the brightness of an LED. Yeah. So the circuit should be up there. All right. Can I just see a show of hands as to who's got it working successfully now? Couple of you, wait, 1 or 2 more minutes. Those who got it working, feel free to skip ahead.
So if you think about it, how are you generating EWM? All it is 1 and 0. How can you possibly generate between them?
All right. So we're going to keep moving along. I'm sorry if skipping past the solution, but feel free to keep on working on that particular problem or on the previous problem even if you need to. and still will answer your questions. Presenting the next slide. So this is all about working along at your own pace, but we'll keep things moving along and interesting. So the next thing I'm going to talk about, and even if you are working on the previous problem, I suggest just listen to this next bit, because if you want to connect an Rgb LED at any point today, you will need to know this next piece of information. So even if you've just arrived, or you're working on another problem, pause what you're doing, listen to this for a second. So this is an Rgb LED. They're great fun. So it's basically 3 LEDs in one. So we've got 4 pins on our LED. It works just like a regular LED, except that you can select any particular color or a mixture of colors. Just be aware that if you do a mixture of colors, it can give you some unexpected results. You might not get the exact color you want, but nevertheless, that's what you can do. The long pin is the common anode, so that when we're controlling this LED, we're actually going to be supplying 5 volts to that pin through a resistor, and then be writing the other pins to low to get our Rgb LED to work. So when we want to choose a color, you actually want to have the current flowing through. You actually write the red, blue, or green pins to low, or invert the analog right to get what you want. If you write them to high, there's going to be no current flowing through. So it's a little bit counterintuitive. The other thing I'm going to say is that the red cathode is in the red part of this Rgb LED, is naturally, without any extra resistors, slightly brighter than the other 2 colors. So to get it so that it doesn't overwhelm the other colors, not only do we have like a 470 ohm resistor into the common anode of our Rgb LED, but we also put another resistor on the red cathode as well, coming back out. So that's why when you look through the slides and see the circuit diagram that I've got next, I've got 2 resistors. One's going into the anode, and one's coming out of the red cathode. So just remember, the red cathode is on the edge next to the common anode, which can be identified as being like the massive electrode in the middle of the Rgb LED, or the longest pin is also the common anode. Anyway, that's sort of important information over, so you can go back to what you were working on. But in terms of how you'd wire that circuit up, I've got it there. So I'm supplying 5 volts to our common anode through one of the resistors, and then I've got the other 3 pins connected digitally to digital pins. I've got 12, 11, 10 there. You could probably do 11, 10, 9 if you want all of them to be pulse width modulated. So we've got a little task for that as well, which is see if you can get the Rgb LED to sweep through some colors. So no analog input, not even analog output necessarily, but see if you can get it to flash red, then green, then blue. Hopefully that should be too difficult. We'll give you guys some time to wire up that circuit. If you're a little bit behind, you can put up your hand and we can help you out.
This is really cool.
Yeah.
How long does the battery on the Robocopter last normally?
You can put up to 2 batteries on it for 20 to 25 minutes.
Okay.
Which is pretty good. Like they're not long. Like it's a lot of energy. So yeah.
Hell yeah.
Yeah.
Super heavy.
No, well, yeah. I mean, these things probably weigh like 1 to 1.5 kilos when they're fully built. So yeah. But things like quadcopters in air, just generally the laws of physics are not kind.
With the actual camera thing,
Yeah.
film thing, is
Yeah.
it part of the whole copter, or is that an add-on thing?
We have an add-on to it because obviously not everyone wants the camera to film, and we put a GoPro on, but we do have the camera stabilizer as an add-on people can get. So are you interested in getting a kit? Do you want one?
My mates have one. They've been working on it for the last few months. I am still on thesis.
Okay.
Be like the worst idea.
All right.
But
Yeah.
it's something I'd like.
Yeah. Well. Yeah. Fair enough.
And for I'm just kind of thinking of the possibilities, because it's beautiful stuff you can do with filming.
Yes.
Landscape
Yes.
system.
Yes. It's
And
amazing.
like getting my head around how much that would cost to set up.
Well, yeah. I reckon have time to work on it. We only do like this sale like once every twice a year.
An Rgb Led because I don't have it in my set. Maybe.
Sure, I'll get it to you in a sec.
Yeah.
Yep. All right. Yeah.
Do you do one of the savings also?
We do.
Okay,
Yes,
cool.
we should.
I'm
Okay.
gonna look into it.
Yeah. No worries. Okay.
Thank you.
Cool.
Because I joined the club last year. So
You don't have an RGB?
yeah.
Okay. Well, that's fine.
I'm sure.
Cheers. Alright. Yep. Um. Yes, you probably could, but you could, I'd recommend just plugging it straight into your breadboard. It's probably more secure. So yeah, just put All right. Anyone got their RGB LED working successfully, lighting up and everything? Task 1 is connecting up the potentiometer. Got a breadboard? We can lend you a breadboard. I'll see. Oh. Use that for now. Just give it back to us. Yeah. Exams and stuff. Uh, I guess make sure that I get round to explaining the final task in time. I'm just going to explain how you would code your RGB LED to switch between things. So I didn't have enough space on the thing to write for red, green, and blue. But essentially, what I've written here for red, you would do for green and blue. So the key thing is it's not too difficult. You've got your pin. Make sure that you pin both of them to outputs in your setup. And then I'm just digital writing it low, which is actually turning it on, and then waiting for a certain specified period of time, and then writing it back to high. And then as soon as I've turned the red off by writing it back to high, I'm turning the green on, and then I delay, and then write it back to high, and then turn the blue on, delay, write it back to high. So that's what the code kind of looks like. It's just a simple digital writing on and off, just to at least for now make sure we can switch between different colors. Put up your hand if you have any questions about anything, need some help. Yeah, don't put it across like that, because all of them are electric magnets. Put it like that. Yeah, it doesn't, yeah.
What is this one? what math does is it changes a number from a certain range into a different range. So this input from this guy gives you a value from 0 to 1024. But your LED needs to get a value from 0 to 256. So it scales it accordingly. So you give it the value there, and the range is, yeah, the initial range and then the final range. So that's a good example. Yeah, like where do you put
Right.
inspection?
I might just check that it is working. At this stage, you have to see.
You got to play out. This is what you're converting from, the lower limit of it, and this is what you're converting from the higher limit. And what you want it to become, the lower limit of it. Ah, I see. Yeah. Look at the example there. Your Mega has so many more.
Sorry. Okay, so you had a common cathode RGB LED. That's really annoying. So that means that it's so you know that one pin which is a common pin. Yeah, sometimes it needs to be supplied push power. Sometimes it needs to be grounded instead of so common anode means supplied without common cathode means it's ground. Anyway, that's yeah. If your RGB LED isn't lighting up, it looks like that some of them may actually be common cathode instead of common anode. In which situation, what you would do is you just treat it like a regular LED, exactly the same circuit, except instead of wiring that common pin to 5 volts, you just wire it to ground instead. If your RGB isn't lighting up at all, consider that it might actually be a different type. But hopefully your RGB should be lighting up. If it's not, we'll take a look at it.
Absolutely right. Let me know if it doesn't work after that. On the color value, it's like a placeholder value. You can change it inside. So at the moment it might be something, and then next one will be a value, a number. It's a variable, right? Is it working? Yeah. Sorry about that. Actually, I think it's only in Mexico. Why should I some Mexico? Maybe have like a neon folder? It's kind of in the folder.
Those 3 lines.
Or you could even have like
There's gold, has a gold band, two purple bands, and one yellow.
This one's completely different. I have a new iPhone.
You use this type.
We didn't get that done.
Then you have statements previously uploaded.
It's actually like standard for probably this much hours. Maybe the best one.
Which resistor are you use on the right again?
Doesn't matter.
Is one of them really big?
Yeah, it just make it a bit bigger.
Yeah. Which is the smaller one? That one's the small one.
One of the
One has green, one's red light.
This is bigger.
And if I put
Alright, so once you guys have got it working, and I will, sorry, going along fast, but the final challenge is the fun one. So once I talk about this, we can then go back and help you fix your other stuff.
It's more like the difference between these
So with the lights, actually, sorry, this is the second last challenge. Okay, so how to use a light sensor. For those of you interested in using a light sensor, maybe just take a break from what you're doing now and see how this works. So what this is like a variable resistor that depends on light. So as light is shone on it, if you know anything about physics, then it acts as the semiconductors inside essentially release electrons and it lowers the resistance across your light panel resistor. So the resistance of this thing varies from like less than 1,000 ohms up to like over 100,000 ohms. So it's got quite a wide range depending on light, and particularly if in the lower sort of spectrum, red light's probably it's more sensitive to than like higher up, but generally speaking, it's visible light. So what we're going to use it with a voltage divider, just like our potentiometer was a voltage divider, to make sure that we can put it in, measure the voltage across. Because we want to power this, but if we just power it and plug it straight into our analog input, it's just going to be 5 volts across there the whole time. It's not going to be useful to us at all. So we need a voltage divider to get this to work. So what the circuit looks like is this. We've got our R1 and R2, except one of the resistors is going to be our light-dependent resistor, right? So this is how a voltage divider in principle works. But generally speaking, we want the resistance of the resistor that we use in series with our light-dependent resistor to be of similar resistance. A great way to do that is to use your rotary potentiometer as a variable resistor, as in use the middle pin and one of the outside pins, and use that as a resistor. We would want our light-dependent resistor to be first if you want to have it so that when it's brighter, the voltage goes higher, because then the voltage across R1 will drop, and V out, which is your analog input, will go up. Otherwise, if you want the opposite to happen, you put your light-dependent resistor as R2. It doesn't matter too much as long as you guys can show some kind of change that you're measuring. So that's what I was talking about before. So you have your light-dependent resistor in series with a resistor, and your voltage out will be something like that. Now, I've got a button circuit here included, but we don't really need the button circuit. All you need is the light-dependent resistor circuit on the right-hand side. So notice that we powered the 5-volt rail of this board from the Arduino and also grounded it. So we've got 5 volts going to our light-dependent resistor. So see if we can get the mouse up. So there's our 5-volt wire going to our light-dependent resistor. It goes through our light-dependent resistor, and then we've got 2 things connected to this leg of the light-dependent resistor. We've got another resistor, and we want the resistance of this resistor to be the large one. So it should be, hopefully in most of your kits, it should be the one with the green on it, like the 5.6K resistor. You'll know because your LED is really dim if you use that for it, as opposed to the other one. If your values are not good, just change resistors. So that side of the light-dependent resistor is going to our analog input here, but it's also going through this resistor, which then goes back to ground. And ground rail is also connected, like this entire ground rail, the blue, is connected back to the ground of the Arduino. So that's what our circuit looks like. So once you get that going, you just analog read it, just like your potentiometer in the first practice example that we did. So And then when you essentially, you can read the ambient light of the room. Obviously, it's more pronounced if you say shine like a light from a torch or like a phone flash on it. You'll notice the change. But with the ambient light in the room, if you put your hand over the light dependent resistor, you should see the values drop. And if you uncover it, you should see the values rise. And if they're not doing that, you do need to, you can adjust the resistor across. The other way the circuit can look like is like that. So here it's the same deal, except instead of the resistor, I've got 2 pins of a rotary potentiometer. And that's really, really useful because then I can calibrate the sensitivity of my light dependent resistor. So maybe instead of using a resistor, you can use your circuit like that, but otherwise it is the exact same circuit. So I'm just going to leave that up on the board. Oh dear. Is this the bad computer?
That's a terrible thing to say. So if you were to off, you give it off. So the on. Right, I thought you wanted to mix version.
No, not necessarily. Just remember that this computer might actually be hopefully not.
Then again, your value
Once that finishes, just hit upload again. This one works on the whole board. Okay. Circuit. So okay, so this is just powering LEDs now. Yes, 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 yes. Ground, yes. Sure. Except with your rotary potentiometer, you want to power your rotary potentiometer. So it needs to actually get 5 volts from, say, oh no, do you have it?
Yeah.
Okay. Sorry. Perfect. And then add a little, yeah, that's it. Perfect. Cool. No? This computer might actually be bad. I'm gonna, do you want to try and move into this computer right here?
Yeah, sure.
Is it working? Is it on? If we don't finish this lab today, I think I'll go through it in more, the last part of this lab in the next lab as well. So, yeah, I don't know why that wasn't approved.
Because only has 2 states. So let's just trade first.
Actually, yeah, that's probably a good thing. If you want to turn off all of these anyway, I just realized the box is below. So, yeah. Actually, yeah, if you do that, that should make the range
Why do you guys on and off? Why?
Any idea why?
Something to code?
No, not actually. This output here, 13, is digital, so it only has 1 and 2.
Oh.
Try to move 12.
I'm not sure that we're going to get everything finished today because this is probably like the hardest out of all the workshops just because it involves so much stuff. But I will show you a quick circuit of the color sensor of what that would look like. So that was using a light dependent resistor. Sensor. By the way, if you're getting values from your light dependent resistor just by printing them out to the screen with your potentiometer, try and get the values to be halfway between 0 and 1023, so around the 500 mark. That's when the sensitivity is most optimal. Now, too much. Color sensor, that's our color sensor. How a color sensor works, I'll explain the concept briefly. But basically, and this can work really quickly, as in like less than a tenth of a second. We shine red, green, and blue light sequentially. The amount reflected back by an object in each situation depends on the color of the object that you're shining on, and by measuring the light reflected back from an object with the light dependent resistor each time, and by comparing how much light is reflected when we shine red light on it, when we shine blue light on it, when we shine green light on it, that's how we can tell what color an object is. So if you have a red object, it's going to mainly reflect red light. So you should notice that when you shine like red on it, it will reflect mostly all of that light back, whereas when you shine blue and green on it, it will reflect much less of those colors back. It does require some complex calibration. That is, you need to shine your red, your green, and your blue on a white piece of paper, determine the maximum, and shine your red, green, and blue on a black piece of paper or a black object, determine the minimum, and then map those values for each of those colors. So it's quite difficult, but I do actually have the file in the Google Drive on this one because it's that complicated. This is including a couple of switches, the electrical circuit diagram of what it looked like. So you see our RGB there with the red powered into the common anode, and then also an extra resistor coming from the red and green and blue. Right next to that RGB, we have our light dependent resistor circuit with a resistor in series that we measure back to our input, and we have a couple of button circuits. So really, it looks complicated, but these are just three separate things. We've got a couple of buttons, an RGB LED that we control, and a light dependent resistor that we measure. So that's quite. I mean, it looks complicated, but it's actually not too bad. It's just the basic couple of components. It takes a little bit to get going, but if you do want to see how that looks, in our Google Drive, in the workshop number 3 folder, which is attached to our Facebook page, or if you go there, I've got here the Arduino color sensor file, which I'll just download now. You can't preview it in Google Docs. And I'm just going to explain how this program works. Wow, that's not helpful.
All these lines are joined across here as well. Yeah.
So this is just get through this is a color sensor. So I did something tricky because we scaled the red, the green, and the blue input values between the reflected values generally tended to be between 550 and 140. That's what I tested. It again depends on you. We had our RGB pins, which were 2, 3, and 4 in this case. We had a couple of buttons, and this was this was a small. This is actually the setup only. So the setup is that we pin mode the RGB pins to output, we pin mode the buttons to input, and we digital write the RGB pins high. That is, turn them all off at the start. And then we had a couple of buttons for calibration. So I've written separate functions for calibrate, but basically, if one of the buttons was pressed, it actually did the reading. So this is probably the first serious program I've shown you guys, where what we had, where this is where sort of the meat happens, is that if digital read, if one of the buttons was pressed, I choose to read the color. I constrain the RGB values between for each of the three values between two things after I read them in. So I analog read them in each time. I constrain them and I map them, and then I flick over to the next RGB pin. So that for loop happens 3 times. And then after that happens, I would then print via some special color logic function, and then I'd analog write to the RGB pin the values that it reflects. With the color logic, I had some very complicated thing happening where it evaluated whether something was twice the brightness of something else when it was returned, and then evaluated how many times that happened. And if it was overwhelming, then it would set one of them. It would set one of them to be 255. It's just a bit of a mess of a program, but it worked. So if you want to plug that in, actually upload that with your RGB connected to pins up the top 2, 3, and 4, buttons connected to pin 5, 6, and 7, and your analog input connected to pin 0, I think it was, whereas analog read 0. Yeah, that program will work to tell you the color. You can analyze that in your own time, though.
Not working.
Why isn't it working? Oh, that's not good.
I'm wondering if there's something